We're looking now at a difference of rates, and this is where you're looking at situations where you might be looking at heating an object while it's also being cooled, births and deaths for a population, liquid going in and liquid going out of a tank. So it's basically you've got two opposing forces, I suppose, or things happening, so at the same time. So what we look at is the rate of change is equal to the rate of increase minus the rate of decrease. And if you think about it in terms of, fluid, you could also simplify this, I suppose, to just say, oops, you're looking at the in minus the out rate. So that's if you're looking at, for example, a tank problem. Or you could also apply that to population, I suppose. So the number of people being introduced into the population minus the people being taken out of the population by death or by emigration. So you've got two things here, increase minus decrease. So we're going to look at an example now where we've got these two different situations happening at the same time. So we're looking at a radioactive isotope which decomposes at a rate that's proportional to the mass m of kilos present at any time t. The rate of decomposition, okay, is 2m kilos per year. So you could think of decomposition as the kind of out part. The isotope is formed as a byproduct from a nuclear reactor at a constant rate of 0.5 kilograms per year. So you could think about this as being the amount in. So it's kind of the amount that you're getting of isotope minus the amount that you're getting out of isotope. And we're looking at a proportional relationship as well for this one. So we know that dt, so the mass of the isotope at time t, is proportional to the amount of isotope present at any time t is, and that's directly, I suppose, related, and I'm not even going to use the proportional here, I'm just going to use the information we have, the in minus the out, which in this case is going to be 0.5 kilos of isotope produced minus the 2m kilograms which are decomposed every year. So we have dm dt equals 0.5 minus 2m, and we could write that a bit more neatly, I suppose. It's a half minus 2m, put everything over 2, so that would become 4m over 2. So we'd end up then with dm dt equals 1 minus 4m all over 2. All we've done there is just made ourselves a common denominator. So that's the first part of part A, which was to construct a differential equation. Part B asks us to solve the differential equation. So we're going to solve dm dt equals 1 minus 4m on 2. I'm going to separate this out. So I'm going to take the dt up, and here what I'm going to do is take all of this over. I've got to take the 2 over first, so bring that underneath and divide it through. Now it's impossible for us to split this m part off from here without bringing the dt and the 1. So this is all really one thing. So let's divide that underneath as well. So we now have 2 over 1 minus 4m dm equals just dt on its own. Now what we can do is we can integrate both sides. So we've got 2 over 1 minus 4m dm equals the integral of, there's really a 1 there, so I'll write that so we can see. This is going to be a log, and it will be 2 lots of log 1 minus 4m inside the log, and we have to divide by the derivative of the bracket of that log as well. Okay, equals t plus c. So now we know we were solving dm dt, so that means we should solve for m. And I'll do that on the next page, so let's take this over. So we've got, these cancel, so we've got negative a half log of 1 minus 4m equals t plus c. Take the negative 2 over, multiply everything by negative 2. And I'm also going to state here that 1 minus 4m has to be positive. Okay, so to do that, I'm just going to state that there, and then so that means that 4m has to be bigger than 1, so m is going to be bigger than a quarter. So that means I can then take away my log sign, my modulus signs, and here I'm just going to do a bit of relabeling. I'm going to call this k. I don't have a k in there, where k equals negative 2c. Take e of each side, because we want to eliminate the log. And here the e and the log disappear. So we've got 1 minus 4m equals, and here we can split this up, is really e to the negative 2t times e to the k. So it's e to the negative 2t times e to the k. And I'm going to take the 4m to that side and take everything over this side. And so to finish off, we've got m equals a quarter minus e to the k on 4, e to the negative 2t. And the thing that I'm going to do here, just to make this, I guess, a nicer looking solution, I know that this is all a constant. So I'm just going to relabel that. So this is going to be m equals 1 quarter outside of 1 minus, I would factor out the 1 quarter. I'll just call e to the k m naught for like initial m. And that's where e to the k equals m naught. So I've just relabeled the e to the k, because a quarter is a nice common factor. There you go. So we've got that solution. That's given us m. Now we go back to our question and see what we need to do next. So we've solved the differential equation. None of the isotope was present initially. And what that means is that when m equals, or I should say when t equals 0, when time is 0, the mass of the isotope is also 0. So let's do that to just finish this off, make this a bit more complete. So this is the general solution. So we know that when t equals 0, m equals 0, so we end up with 0 equals a quarter, 1 minus m naught e to the 0. Now we can find m0. So cancel that out because of the 0 there, so we then have 1 equals m0. So that's nice and tidy. So that means that our particular solution is m equals 1 quarter of 1 take away 1. You don't really need to write the 1, you can just write the e to the negative 2t. So that's our particular solution. And I'm just going to copy that over onto the next page, because that's the one that we can actually work with. Alright. And I'll write underneath, or next to that, is our particular solution. Alright, so now we have to look back at our question. You can see we've constructed the differential equation, we've also solved the differential equation. Now we have to sketch the graph of m against t. Alright, so the way that this would work, if we have a look, what I want to look at here is just expanding this out, a quarter minus a quarter e to the negative 2t. Now the behaviour that will happen here as t approaches infinity, this is going to become, m is going to approach a quarter minus 1 on 4, and this is underneath because it's a negative power, effectively infinity underneath. So this will approach 0. So basically what you're going to find that as t approaches infinity, m approaches 1 quarter, but it won't quite get there. So that tells us that we have some asymptotic behaviour in this particular graph. Okay. The other thing that we know is that we know at the initial time, 0, that m was equal to 0. So that tells us a point on our graph is 0, 0. So we've got an asymptote at m equals a quarter, and we've got a particular point. Alright, so what we can do now is graph this. So we'll put some axes down. we've got M, which is the mass of the isotope, and T. We're only interested in positive T, so we're only interested in the first quadrant. We have at M equals 1/4, so at this point here, we've got an asymptote, and we know that we have a point at 0, 0. Now if you wanted to, you could also put another point. You know, you might take, I usually do T equals 1, because it tends to be quite a nice one. So in this case it won't be, doesn't matter. So that would be 1/4 of 1 minus e to the negative 2. So I'm just going to put that in, put a point 1 there, and 1, and then minus 1/4 e to the negative 2. Oops, I shouldn't have the t there anymore. It's been negative 2. So that would be another point on the graph. And the nice thing is, because we know that this is an exponential, it has to have a sort of bent shape in some particular way, one of these kind of shapes. And because we're approaching an asymptote here, it must be the first shape that I drew. So it has to go kind of like that, and then approach the asymptote but never touch it. All right. So that's the type of graph we have for this situation. That's our graph of m equals 1/4 1 minus e to the negative 2t. And the last part of this question tells us, or asks us, how much isotope is there after 2 years? So that's when t equals 2. So when t equals 2, what does m equal? So we can substitute that in. So we've got m equals 1/4 of 1 minus e to the negative 2 times 2. So 1/4, 1 minus e to the negative 4 is m. And then to solve this one, it's easier to put that into the CAS. So I'll put that in. So let's solve, use the solve command. M equals 1/4 outside of, I might actually just put brackets around that. Put a multiply in there. 1/4, 1 minus e to the negative 4. Oops. E to the negative 4. And we're solving that for m. You could just put the equation in, by the way, it would work either way. And then push enter. So we get an approximate, it's m equals 0.245. So I'll just put that into there. Is that m? And remember that what we're looking for here is m, which was in kilograms. So it's always worth going back and just making sure we know what we're actually doing here, which is m kilograms, and t years. So what we could say then at the end is, after 2 years, approximately 0.25 kilograms of isotope exists. So you've looked at the time and you've factored that into your solution for the differential equation. So a good example again of constructing a differential equation, finding a solution, graphing that solution, always looking at asymptotic behaviour, particularly as your independent variable approaches infinity. That's a good way of finding asymptotes, and then using substitution to find a solution for m when t is equal to 2 years.